My name is Ion Marqués, and I come from NEM Solutions. The title is Predicting Failures on Complex Machines. So let's see what this presentation is about and what NEM Solutions is about. So we are a company that provides complete management solutions to business responsible for the operation of and maintenance of multi-system assets, of complex machines. Nowadays, the situation is that these companies have thousands of assets, and then they are generating massive amounts of data. So what we'll see in this briefly 50 minutes, it's first, we'll see which are the client's needs. Then we'll see what is our approach to fulfilling these needs via big data, of course. Then we will see very briefly the overview of the solution. We'll continue viewing in more detail the engine of the solution, the streaming solution that we have implemented, that we are actually now implementing. And finally, we will wrap up with some lesson learned, how to say. So let's start. In NEM Solutions, we work with two industries, mainly with rail and with wind industry, with wind turbines, energy industry. So regarding train, there is a high demand of efficient and sustainable transportation systems, and the high-speed and urban transportation needs are on the rise. It happens the same with wind energy. There's an increase in energy needs, and the on- and offshore wind turbine installations are growing quite steadily. So there's a need for productivity, reliability, and continuous improvement. So our approach is to provide business and knowledge, avoiding surprises and having the business under control, in order to avoid a traditional reactive approach where the business plan tends to fail and where unexpected things happen and make you ultimately lose money. So what we provide here is, concretely in the wind turbine industry, usually they have these SCADA or EAM systems that collect all the data. What we provide is another layer of technology called Aura, which is the appropriate tool for on-time decision-making. It is the technological groundwork for being able to take those decisions. So on top of that, what we provide is a know-how. So we can have a business-driven data management, generating knowledge and business benefits. This is an overall view of our company approach. So Aura, concretely, the technical solution is what I'm going to talk about here. This is a brief overview of how we work. So we have some data sources. It can be a train, it can be a wind turbine. And what we do is we build a normality model. It's the core of our solution. And from that model of what it is normal, then we get real-time data, and we compare it with the normality model. And we can predict on time when a certain component of a certain machine is going to fail. We are trying to be proactive on this term. So what we get from this Aura system is, first, we get a projection to the future from the data, and we generate knowledge. So the client gets not only that, okay, it seems that this component is going to fail, but it gets also knowledge about how the components of these complex multi-asset complex assets behave. So let's go to it. Now, the problem is, how do we transform this Aura technology, which is in production, which has been working for some years, into a big data scalable solution? Here we can see an overview of what we do. As you can see, let's see if here we have named things because it's important to name things. So we have the shipper via Flume, where it's on the client side, and then our solution has an ingestion service. We use Kafka for queuing between the services. Then we have what we call a crane, which is the data decoupling module. We persist on HBase. And finally, here on your right side, you can see the engine, which is the streaming machine that runs mathematical operations and complex machine learning methods, which is built with Storm and uses Redis and HBase for persistence. So when we try to approach this big problem, we think that the key point here is the engine. It's the most complex of all. So let's see how we tackled it. So what was our first approach? we thought, OK, we have some calculations that we have to do. They have relationship between them. It's like a graph. So we can translate these calculations to a topology. So if each topology node is a computational unit, like an arithmetical operation, a machine learning algorithm testing phase, or a symptom calculation, or whatever, we can translate each computational unit into a storm vault. So we build a big, at least for us, a big topology, complex topology that is doing all the computation that we need. It is helped by Redis and Kafka. So we have all the data at once coming in a single spout. Then the spout works, broadcasting all the information to the vaults. And finally, we get symptoms. This is problematic. First of all, what we saw is with one master spout is a big bottleneck for the problem. So if a vault fails, all the data must be again sent by the spout must send all the data back. So this was not a good approach. So of course, we failed. We tried again. Let's see what we can do. So we had a second approach. We said, OK, let's put one spout for each variable or for each asset that we are monitoring. But again, there was too much communication for our case. It was not effective, because if the data have to go from the spouts here to the next layer of vaults, as you can see, there is many messages being sent. There are some vaults that are waiting for other vaults to compute their part in order to do their job. It seems like it was a very big problem how to manage the communications between the vaults, how to tune Storm, which is a bit complicated. So it didn't seem to be the best approach. So what we did next, how can we put this problem into Storm, was this. This is the approach that we last used. And the data coming, what we did is, let's have this big topology, and let's try to define subgraphs that are not codependent. I mean, if I have to process in this topology 20 nodes at the same time, there are no dependencies between them. Let's build a node. And inside that node, I will define some tasks. And those tasks are the ones being parallelized by the Storm engine. So what we did was simplify the topology. And by simplifying the topology, we were able to reduce, as it's quite obvious here, we can reduce the communication overload, and it's easier to fine-tune the topology. So we need fewer nodes, and we assign, in this case, one executor per task. That's what we did. So it offers the same parallelization capabilities than before. There's less communication, and it is well adapted for small clusters, because in our case, at least when we are doing these proofs of concepts, you don't get to say, OK, give me a 200-node cluster in Amazon because I want to do some tests. Of course, you have some constraints, and it seems like this is a good approach. So in this point, we had a better performance. Our topology, what we thought was the problem, like the directed graph, was embedded into Storm in a sensible way, in a way that actually it really worked. So what we had at the beginning as a company, we had the knowledge about the industry's needs, and we had the machine learning methodologies to extract useful information, and this knowledge and these machine learning technologies were actually working well, but in a non-scalable tool. So what we needed was the means to make that product capable of processing massive amounts of data and to solve the key point, which was how to embed these algorithms into a scalable streaming framework that could be Storm, could be Spark, or Apache Flink. So what did we learn from all this? First of all, the points that I want you to take from here is that the industry demands tools that assist in making decisions, affecting lots of complex machines. For example, in our case, we have a company that has 2,000 machines, complex machines, that each one of those has many small components, many complex components working at the same time. So how can I monitor 20,000 wind turbines at the same time? It's difficult. That's what we needed to solve. So In order to meet that particular demand, we needed something more. You need something more than some amazing visualizations, which are very important, and simple data mining methods or simple statistical analytics, which also are important. But you need something more that derives from the knowledge that we have about the area. In this, for example, if we are talking about wind turbines, the knowledge that we have about the machines, about wind, about how they behave. And also, we have to have all the knowledge down to how to implement a simple storm vault in Java. So technically, this was a challenge. And from our experience, we can say that using Kafka, using Storm, Redis, and HBase, it seems to be a winning choice. Of course, there is no freelance, and I think that I'm saying the same again, but you cannot have one solution that fits for everything. So you have to know really in which area you are working with kind of data, what the client is really asking you in order to find the right tools. What we did, and this is our experience, is to translate your algorithms into a path that the data will cross. So like, it can be a directed graph or a topology. So try to translate all this process into, from the data's point of view, do a data-driven approach to the problem, and then try to simplify and fail and try again. I mean, it's a failure and trial process. And the last point here, and I think it's one of the main points that I want to make here, is that in order to be successful, in order to meet the needs of a top 3 company that manages lots of complex assets, is to have a team that must really know the problem, has knowledge about the problem, from how the heat in the wind rotor behaves to how failures in a storm propagate. So it's really important, I think, in order to build a big data tool that really is able to help the client make better decisions that finally they translate into money savings. It's really important to have people that really understand, really work on every single point of that data, from how that data is created, because the wind, how the wind behaves, how the turbine behaves, the machine itself, depending on the wind, until you go down to the lowest level of abstraction. You're working with the different programming languages, the different big data platforms like Storm, HBase, or anyone else. So I think that is quite important to get from here. So overall, I hope that you have taken a small view of what we do here and how we tackle this big data problem. If you have any question, I left some minutes, so you can ask anything if you want, or if not, we can talk later. Here you have my contact and the contact of the company anytime you want. Here we are. So thank you very much.